everyone, and today we will talk about Lecture 5, Part 2, using subsedients and proofs about that. So I just want to quickly go over to this and... Oops, nope. What lecture unit is this? What lecture unit is this? Oh, this is Lecture 9 only. This is the lecture I'm on right now. So we'll get all this stuff later. And I've actually went through all of these. A lot of annoying proofs. But this is pretty useful. So let's just look at Lecture 5. See Archimedean property and density of the rationals. See, there's this Q. This is like the extension of the simple fact proof. So this is here. There's no remark here, so this is what is good. Proof this is left as an assignment and SSI. Oh shoot, that's an assignment. Okay. And we'll see all this. So now let's talk about this definition and stuff. So we actually told you this last time. Oh yeah, so this is the soup one. I won't give the remark. You can just flip it. Assume S is a subset of R. It's not empty and bounded above. Then X equals to soup S. And this is the if and only if symbol. So if and only if X is upper bound. I'm not even going to write that. It's obvious. Super nums are at least upper bound. And there's a second one. This is actually important. There exists an epsilon greater for all epsilon greater than 0. There exists a y in S such that x minus epsilon y is less than or equal to x, and the converse can be said, but you can look at the previous lecture for that if you want to see that. So theorem, this is a new theorem. This is not a useful theorem. Well, it's not anything like important. It's just like, okay, you could call this a theorem, but it's not like those theorems where they give you much information. This is just like a fact, and you want to prove it. The supernum of this set equals to 1. So what does this set look like? Well, this is 0. This is 1/2, 2/3, 3/4, and we keep going on. And we can see it's obviously 1 because it's going to keep approaching 1. If you see our limits video, supernums are actually kind of similar to limits, and we'll actually get to limits in lecture 6, the very next lecture. So equals to 1. Now how does this work? Well, here's another cool tidbit. This is actually lecture 8. I'm already showing you guys limit stuff, even though, guys, by the way, you don't have to know about this. You will have to know about, I will show you how limits work in lecture 6. And then it's the same thing as this. And this is 1, because everything's 1. And this is 0, because like 1/2, 1/3. So 1 minus 0 equals to 1. So obviously this is 1, and the supernum's 1. But we haven't got to that. You're going to use some stuff. So we're going to denote this by F. So 1 is obviously supernum F, but since 1 over n for all is less than 1 for all for all n in natural numbers, then there should not be n. 1 is our upper bound for this F set. Oh yeah, by the way, it's the same definition there. So now we're going to start using epsilon. Let epsilon be greater than 0, then there exists an n in natural numbers, Archimedean property such that, well, this is a different way of writing it. 1 over epsilon is less than n. Then one minus epsilon is the 1 minus n. This is 1. Thus, there exists an n in natural numbers such that 1 minus epsilon is less than 1 minus 1 over n, which is less than 1. I should start putting these squares. Oh, oops. Proof done. So the professor actually puts a square after the proof, and I'll do one over here. Oh no, it's not done. Here, there's another definition and another proof. So if you saw the x plus a thing, you'll see what I'm talking about. For all x real numbers and a subset of real numbers, we define x plus a to equal the x plus a, where a is an element of a. So basically it's like scalar addition. So if you want to do 5 plus the natural numbers, you add 5 to everything. So the set will be 6, 7, 8. If you want to do 4, like to see the 5, like 5, 6, 7, 8, 9, 10. So basically just adding specific value to each of the amounts. This is what we define that. Multiplication is very similar, as you probably expect. You'd expect it to be this. And yep, this is what's defined. So now we're gonna have some theorem. This is an important theorem now. So not like finding supernom. This is an actual theorem, important theorem. If x is if x is a real number and a is bounded above, or just ba. In fact, I think I should stop writing this. You guys can probably already imagine this. Then x plus a, I don't have to write that, is bounded above ba. So it's the, I'll start going a bit harder on you guys. A, remember x is part of the real numbers and a is the set here, equals to x plus sup a. Now we don't know what happens with the complex numbers, but hey, we don't care about that. It's real analysis, not complex analysis. Complex analysis is much more harder. It talks about complex variables. And a very similar proof over here, except x has to be greater than 0. And a is b. Oh yeah, we're also going to assume x is real. We're just going to assume that. Like, just assume that. And a is bounded above. Then a is bounded above. Oh yeah, the first one's also bounded above. And sup of a is equal to x times the sup of a, the original set. So these are some pretty cool properties, and now we're going to prove them. And the proof is a bit long. You kind of have to get used to these kind of proofs. Nice hospital truck out there. I'm just joking, but that noise. Hopefully nothing happened. Oh, so number 1, suppose x is an r. I'm not actually going to write it this time, and a is ba, or bounded above. and soup A exists in R. So soup, fine, I'll put this, soup A is part of R, exists in R, whatever. Because that's the LUPP. Then there's a bound property. Then for all A in A, little a, for all little a in this big set, big A is less than or equal to soup A. Because that's the definition of, that's the basic definition. Again, our basic intuitive view, which equals, implies, that was implies, I didn't see it, for all A in A, x plus A less than or equal to x plus soup A. X plus soup A is an upper bound for XA. So let epsilon be greater than 0. That has to be there. Then my previous theorem, the one, and my previous theorem not being like the previous, like the important one, like the definition of, then by definition, there exists a y A such that, and by the way, this soup A minus E, oh my god, epsilon is less than y. Why did they put Greek letters? Which is less than or equal to soup A. Which implies there exists y in A such that x plus soup A minus epsilon then plus y, which is less than or equal to x plus soup A. And he was about to skip this proof, but he covered it very quickly. So I'm going to share it to you. That's my gift from me to you. But I'm going to go through this quickly, and I'm not going to write much down. And even the epsilon at this point. So suppose x is greater than 0 and a is bounded above. So x greater than 0, a is bounded above. Then, for all a, little a, in a is little a is less than or equal to soup big A, which is less than, which implies for all little a in big A, x times little a is less than or equal to x soup big A, which implies x soup big A is an upper bound for x big A. Let epsilon be greater than 0. Then there exists a y in big A such that soup big A minus epsilon divided by x is less than y, which is less than or equal to soup A. Then there exists a y in A such that x times soup big A minus epsilon less than or equal to, what the? Sorry. So we know that. So then there exists a y in A such that soup big A is less than epsilon divided by x, which is less than y, which is less than or equal to soup A. Then there exists a y in A such that x times soup big A minus epsilon is less than xy, which is less than or equal to x soup big A. Then, which implies there exists a z in x big A such that x soup big A minus epsilon is less than or equal to z. Thus, x soup big A equals to soup xa in A big A. That was a bit confusing because I didn't write anything down. Theorem, and of course another proof, because At this point, with every theorem, there's a proof. Every theorem, there's a proof. But after that, we get to absolute value, which sounds super fun right now. It will be, but after some time, we'll get to triangle inequality, then absolute value will just be torture for us. So many absolute value brackets, so it's just annoying. It's the easy concept, but it's just so annoying. So, theorem. With our only happiness, I wish I can draw on this thing. A, B, subsets of the real numbers, with A bounded above and B is actually bounded below. And for all x in A, that was the worst x and worst upside down A. And for all y in B, x is less than or equal to y. And then sup A is less than or equal to inf B. Pretty interesting. And the proof, how long is this proof? Oh, this is a very pleasant proof. Not too long. So for all x in A, x is less than or equal to y, which implies y is a upper bound. For A, which also implies sup A is less than or equal to y. Thus, for all y and B, sup A is less than or equal to y, which implies sup is a lower bound for B. Sup A is the lower bound for B. So sup A is less than or equal to inf B. And now I'm going to put that square over there. Put a nice looking square over here. Not a very great square. Why did I say nice looking? It's not very nice looking. Absolute value. I'm tired today. Okay, so we'll go through absolute value and its theorems. And I feel like probably skipping the proof and ending it this with. And then we'll just talk about the uncountability of the real numbers. And, yep. So, absolute value. The reason is because I named this video using sups and infs, or the precise definition of sups and infs. I don't know what I'm going to name it yet, because I'm still making it. But I shouldn't spend that much time on absolute value. And the proof itself is a bit tiring. And no one's going to want to see, oh, that's so long. If x is R, if x is part of R, if x is real number, x absolute value is x. So x is defined as this. This is actually a definition. And a pretty nice one, not that bad. Good definition. And now we're just going to state the theorem and we're going to be done. Proof is a bit weird. For all x in R, x is greater than or equal to 0 and the absolute value of x equals to 0. For all x in R, if absolute value, if the absolute value of x is greater than 0, the absolute value of x is always greater than 0, and the absolute value of x is 0, if and only if x is 0. So basically this is saying that the absolute value is always non-negative. And if x equals to 0, then the absolute value is 0. Very easy proof. In fact, I don't even feel like proving that. This is also very obvious thing. These are all super obvious. But for all x and r, absolute value x equals to absolute value of negative x. 3. So for all x, y, and r, x, y, the absolute value of x times y equals the absolute value of x, absolute value of y. And 4 is a special case of that, so I might not even mention it. But you know what, I'll just say it. X, absolute value of x. You know what, what's the point? Who cares? And this is true for even powers, I'm pretty sure. Odd powers, I'm not going to think about it. My brain's so brain dead right now, I don't even want to think about it. And that's not a great situation to be in when you're doing real analysis. I think I just got brain dead from that proof. If x and y are, then the absolute value of x is less than or equal to y, which implies negative y. So this makes sense. Theoretically, if you think of it, I can actually think of it. And the statement about exponents, that doesn't work with odd ones. So I'm actually thinking now. For all x and r, so it's less than or equal to this. And the final theorem, the last theorem, I forgot there was one tiny theorem. What does this say though? I can't read it. It's a triangle inequality. It's one of the most important theorems ever, and I can't read it right now. This is the worst situation I've ever been in. This is very important. Like, he uses this. Oh, thank God, I think I got the... Oh, yeah, we got the triangle inequality, baby. We got some part of it in lecture 6 on my notes. So here, this is the triangle inequality. There's actually something in the middle, but I can't read that. That's the problem. But here it is. Most of it, anyway, the important part. And to look a bit at lecture 6 where we think about it a bit. Let's think of this as vectors. So if you don't know what vectors are, well, this is basically how vectors operate. And then you see the triangle made by these. Obviously, 2x plus vector y is greater than vector y. But this is basically oh yeah, but the only problem is, how does that make any sense? How can that be a triangle? Well, anyway, this is a triangle. That's why it says less than or equal to. See, in this situation, and like usually triangle inequality, it's for an actual triangle, but over here, it's going to be less than or equal to. This time it works for the equal to. So less than or is obviously, so this is obviously less than or equal to this. And you can do the same thing here. It's obviously less than or equal to x already is there, y is there, and then another y. Obviously less than or equal to. So all of them works for the less than or equal to situation. And now we're done. So that was just a visual thing of the triangle inequality in the next lecture. So I'm not going to cover it since I already have covered it now. So anyway, goodbye.